complex ion equilibria. I just realized this morning that I should probably move experiment 26A to after this section. Chapter 26, we talk a lot about complex ions, but we do talk about them a little bit here, and it might make it a little easier to understand what's happening in 26A, the experiment. That's all just me talking out loud, thinking out loud. Okay, so transition metal ions are often good Lewis acids. And remember, a Lewis acid is an electron acceptor. Water molecules can act as Lewis bases. Lewis bases are electron donors. So remember, a water molecule has two lone pairs on the oxygen. Those are the electrons that it can donate to the Lewis acid. So the water molecules can hydrate transition metal ions. So if we think about silver ions in solution, there aren't actually just silver ions floating around by themselves, kind of like there aren't H plus ions floating around by themselves. The silver ions are hydrated. So in this case, we have two water molecules that are going to come, and they're each going to donate an electron pair to the silver ion, and this is more stable than silver ion by itself. So this is called a complex ion. So a complex ion has a central metal ion, and then it has one or more ligands. That's a new word probably, ligands. So we have one or more ligands that is bound to that, and often this is a Lewis acid base type thing. So the ligand is a neutral molecule or an ion, it can be either, that acts as a Lewis base with the central metal ion. So here, water is the ligand. In our green salt experiment, come on. And then we figured out that there were 3 K pluses. This is a complex ion. There's a metal ion here, Fe3+, and the ligands are oxalate ions. And the oxalate ions with all those oxygens have lone pairs that they can donate to the iron. If a stronger Lewis base comes along, it can displace the water. So here we have a silver ion that has 2 water ligands. We have a complex ion. If we bring in a stronger Lewis base, ammonia is a stronger base than water, it can displace the water. So it's going to push the water aside. No, move aside. I've got this. I'm better at donating these electrons. And so then we get the silver with ammonia instead. Usually we just leave water out of the equation. So pretty much all of these metal ions that we always just write as this, they are just like the hydrogen ion. They're going to be hydrated in solution. Most of the time we do not care how many water molecules hydrate them, but that's what happens. So this is like the, when we do like HCl plus H2O, right? We get H3O plus Cl minus. Well, a lot of times we leave the water out because it makes the equation simpler. Okay. So that's what they're showing here. So we have this silver ion, and it will interact with 2 ammonia molecules, and those will form a complex ion. Now we have another K, another equilibrium constant to add to our collection. This is Kf, a formation constant, and this is the equilibrium constant for the formation of this complex ion. And you see these formation constants are typically very large, because these complex ions form, they really, really like to form. So Kf then would be equal to the products divided by the reactants. And again, we have this 2 coefficient, so then the NH3 gets squared. Any questions? It's kind of like stuff we've done before, but it's a little bit different too. So here's a list of a table containing formation constants. This is from in chapter 18. There's another more extensive list in the appendix of the textbook. And so if you need a formation constant, you just go look it up. Notice that some of these are really big, like cobalt and ammonia, 10 to the 33. Mercury and cyanide, 10 to the 41. Iron and cyanide, 10 to the 43. That's huge, right? It's really, really, really big. It's bigger than Avogadro's number. Yeah. Okay, so let's try to do a problem with this. You mix a 125 milliliter sample of a solution that is 0.0117 molar in nickel chloride with a 175 ml sample of a solution that is 0.25 molar in ammonia. After the solution reaches equilibrium, what concentration of nickel remains? And the formation constant is given. So a real basic question is, how do I know what complex ion forms? Well, you've got nickel and you've got ammonia. If they don't tell you, like they are implying here, you go look for the formation constants. A lot of times there's only one complex ion between those two things, so there you have it, that's it. So this is the complex ion that forms. So a good place to start is to write the chemical equation showing the formation of that. So we've got nickel, 2+, and we've got ammonia, aqueous, and this is an equilibrium, although it lies very far to the right. And then this is what we're forming. This guy right here. And then we need to balance the equation. So the complex ion has 1 nickel and 3 ammonia molecules. No, 6. Where did that come from? 6 ammonia molecules. 6 ammonia molecules. Okay, so there's our balanced equation, right? And then let's just write Kf is then equal to the product divided by the reactants. NH3 to the 6th power. It does seem high. It is high. That's what it is. Well, let's write down the information that we're given. We've got nickel chloride. So what you're thinking in your head is, well, that dissociates into nickel and chloride ions. And we're not interested in the chloride ions. We're just interested in the nickel. There's 1 nickel ion for every one of these. So I've got 125 milliliters of the nickel solution, 0.0117 moles per liter. And the ammonia, I've got 175 milliliters, and it's 0.250 moles per liter. These are going to react and form this, and this is a lot like that first step in a titration type of calculation, where we have to look at the stoichiometry. Our equilibrium constant here is very large, right? And so instead of just looking at initial concentrations and then trying to figure out the change that goes forward, we're going to say, well, this is really big. Let's say that it all goes forward and then comes back a little bit. So we'll make a stoichiometry table here. And so remember that millimoles per milliliter is the same as moles per liter, right? Pull my calculator out of my pocket. So for the nickel, moles initial would be 125 times 0.0117. So 1.4625 millimoles. And for the ammonia is 175 times 0.25, 43.75 millimoles. And initially, we have 0 of the complex ion. So I'm making a table here. Then we're going to look at the change. High equilibrium constant goes to the right, so we're going to react everything. Which of these is the limiting reactant? Well, we want to say nickel because this number is so much smaller than that, but we do need to watch out for coefficients here. But we can eyeball this and see that that is more than 6 times this, right? So if this is the limiting reactant, then we're going to lose 1.4625 of that. And here, we're going to lose 6 times 1.4625. Do you understand why? Because this is going to take 6 moles for every 1 mole. And then we're going to gain, and there's a coefficient of 1 here, so we're going to gain 1.4625 over there. So moles after, this is 0, 43.75 minus 6 times 1.4625, 34.975, 1.4625. Now we can make an ice table. We're going to totally run out of room here. That's okay. So we've got nickel, we've got 6 ammonia, and we've got our complex ion. The ice table has to be molarity, right? Here we've got millimoles. Well, 0 millimoles is 0 molar nickel. How do we get the millimoles here to be molarity? So 34.975 millimoles of ammonia, and I need to divide by the volume, the new total volume. So this is very much like that pH titration. So we've got 125 plus 175. I don't need that anymore. Milliliters. .1116 looks like, we're going to have 2 or 3. So I'm going to just go with 5 here. Millimoles per milliliter, same as moles per liter. So my ammonia then is 0.11, 11658. And the complex ion is its millimoles divided by that same volume. 1.4625. Zero 0.0048. Ooh. 75. It's getting kind of messy here. Any questions? Yeah. So I got this number the same way I got that number. I'm going to take the millimoles of the complex ion and divide by the new volume. So this is looking and sounding very different, but this is the same process as for a pH titration. Remember where we had our weak acid and we add base to it and we say, well, let's react it all, and then we have to find the concentrations with the new volume. That's the same thing that we're doing here. Now we look at the change. The reactant side has a 0 on it, and so the only way this can go is to the left. So this is going to be plus x, and what's this one going to be? Plus 6x. And then this one's going to be minus x. This is the secret to that problem that nobody could do on the exam. If we took the initial amounts here and did an ice table, and then we're looking at the reaction going forward, the problem is that then x is so close to one of the numbers that you're subtracting it from that the calculator can't handle it. And that's why you get no sign change error. And so that example in the exam had a equilibrium constant of 10 to the 20, I think, or something like that. Huge, right? So you had to recognize that you push it all to the right side, and then you do it. And some people are going to say, well, that's not fair. You didn't teach us how to do that. Yeah, that was a critical thinking problem. You had all of the pieces to put it together, and I totally get why nobody got it. But that was the challenge problem. Okay, so then equilibrium, we've got x, got 0.11658 plus 6x, got 0.004875 minus x. Okay, time to make some space. We can then take these expressions, plug them into this equation, and I just erased what KF was. You've got it on your paper. What's KF? Times 10 to the what? 8. Okay, thank you. So that's KF, and that's going to be equal to the concentration of the complex ion, 0.004875 minus x, divided by x times 0.11658 plus 6x to the 6th power. You can use your solver to do this. Sometimes the solver will run out of digits. It can only handle so many characters, and you get to the end and it won't let you enter anything else. Well, then go back and remove some things. Do you need decimal point 0 here? No, you could delete that. It's not going to change anything. Do you need the 0 before the decimal point here? No, you could delete those. And then if it comes down to it, you can just start deleting the last digits of these guys until it all fits. So you can use your solver to do this. But we can also use X is small, because X is going to be very small. So you go ahead and do your solver if that's what you like. I'm going to do X is small, so that means that that is 0 and this is 0. And so I'm going to end up with X is equal to 0.004875 divided by 2 times 10 to the 8th and 0.11658 to the 6th power. Double check that X is truly small. Less than 0.2%. Max iterations error. Okay, so if you get that on your calculator, did you start with X equals 0? Okay, so I always recommend starting with X equals 0. If you start with X equals 0 and you get max iterations, that says, okay, there's a limit to how long I'm going to keep working on this problem, and I'm done. So your starting value is too far away. So then we need to give it something else. So a lot of times if you do 1 or -1, in this case, since we know it's going to be a positive number, I would do 1 or something like 0.5 and see if that works. Anybody else have questions? Does that work? It didn't like 1 either? Okay, let me talk to it. Hello, nice little computer. It is a computer. Okay. Double check.
I definitely could have put something on. I didn't actually.
It looks like you got the equation there correct. So I'm going to try 0.01. Please. Oh, I got a no sign change error that time. That's different, right? That's a different error.
Yeah, that's what I got when I put 1 in.
Is anybody else getting their solver to work? Or are you having trouble? Did you get yours to work? No. Okay. Okay, let's try, let's try 0.5. Max iterations usually means that it can be done. No sign change error. Oh, got the no sign change error again. It could go either way. I'm going to try -0.1. I don't think it's going to like this either. No sign change error. Okay. I'm going to try 0.00000001. Error. Okay. So I already did this calculation, and so I know that that's a really small number. And so I'm like, okay, I'm going to help you out here. I'm going to get really close to what you're supposed to find. So I put in a really small number, and that time it worked. Yeah. Now, if you are taking one of my exams and your calculator is doing this to you, please come and ask me. I can help you talk to your calculator, okay? This is one of those situations where it turns out it is much simpler to do x is small than to use the solver. But the solver does still work, right? You may just have to fiddle with it a little bit. If you're not strong in algebra and you can't take this and rearrange it correctly, then this is going to get you the wrong answer anyway, so you might as well mess with your calculator a little bit and get the correct answer. It's not going to give you a wrong answer. It'll give you no sign change or max iterations, which means just try again with some other number. Any questions? Other questions? Well, that's interesting. I got 9.7, and it got 9.6. I'm not going to worry about that. Okay, we talked about the common ion effect as having an effect on solubility. Complex ions have often a huge effect on solubility. So the solubility of an ionic compound that has a metal cation that forms complex ions will increase in the presence of Lewis bases that complex with the cation. The solubility of an ion that forms complex ions will increase when you add that ligand to the solution. The most common Lewis bases that will increase solubility are ammonia, cyanide, and hydroxide. So here we have complex ion formation. We have ammonia plus silver chloride. Remember, the chloride is just a spectator ion. So the silver can get hydrated a teeny tiny bit, or we can also look at the, actually this is what we want to do. We've looked at solubility, right? And so we look at the solubility of silver chloride. And it's going to be like this. And you have a KSP. So if we have silver ion and we add chloride, it's going to, at some point, precipitate. So you get that equilibrium established, and the silver ion is going to be very small in concentration. And so this is your solution at equilibria. If we add ammonia to this, the ammonia reacts with the silver ions, and the silver ions become this complex ion. The silver ion is no longer just the single silver ion, no longer the silver ion that's in this equilibrium. So this is in effect removing the silver ion. What does that do to this equilibrium? It's going to shift it to the right. So you took my silver away. Well, I'm going to shift over and make more just to get back at you, right? So adding the ammonia that complexes with the silver ion pulls the silver ions out and allows more silver chloride to dissolve. Does that make sense? So the normally insoluble silver chloride, if we add ammonia, then it can take these silver ions and complex them. And when it pulls them out, then we also have chloride ions. I've been using these slides for years, and there's another typo I just saw. You see what it is? Cl plus? What? Cl minus. I had to fix a typo on the selected precipitation one because at the end it said the wrong cation was left. But you labeled the colors. Yeah. Everyone makes mistakes. So because the ammonia occupies the silver and occupies it to a great extent, it's going to take all the silver and so then this solution will completely clear up and there'll be no solid left because all the silver ions are complex, so they cannot precipitate with chloride. So adding the ammonia changes the equilibrium constant for the dissolution of silver chloride by a factor of 17 million. That's big. So the almost insoluble silver chloride becomes really quite soluble. And so we can look at these two processes separately. So here's our silver chloride dissolving. Here's our KSP for silver chloride. The silver ions that are formed react with the ammonia that has been added to the solution and form this complex ion, and this is the formation constant. We did this way back in chapter 16, I believe. You've got two equilibria, two equilibrium constants. If you add the two equations together, you multiply the equilibrium constants. So when we add these together, the silver gets canceled out because all the silver that's being formed reacts with the ammonia to make this. And so this is the equation that we're looking at now. To find the equilibrium constant for this equilibrium, we take KSP times KF, and we get 3 times 10 to the minus third. So now we could do a calculation involving ammonia and silver and figure out, say, well, what is the chloride concentration at the end? Any questions? Yeah, just make sure I didn't. Okay, which compound, when added to water, is most likely to increase the solubility of copper sulfide? Sodium chloride, potassium nitrate, sodium cyanide, or magnesium bromide? Well, let's go back here. The most common Lewis bases that increase solubility are NH3, Cn minus, and OH minus. I don't expect you to have those memorized, but a homework question, you can go back and look, right? That's the nice thing about the homework questions. So which of these is going to increase the solubility? It's the sodium cyanide, because chloride, nitrate, and bromide are not going to form complex ions with the copper. Oops. Yeah. Amphoteric metal hydroxides. These guys are weird. So a lot of metal hydroxides are insoluble or only slightly soluble in pure water. When we look at the solubility rules, we see that the alkali metal hydroxides are soluble. The alkaline earth metal hydroxides are somewhat soluble, and pretty much all the other metal hydroxides are not soluble in pure water. But these metal hydroxides, some of them at least, are amphoteric, meaning they can act as acids or as bases. So that will increase their solubility. So here we have aluminum hydroxide, a solid, and when we add hydroxide to it, we can form this complex ion, which is soluble. So AlOH3 is soluble at high pH, where we have a lot of hydroxides, and it's also soluble at low pH, but it's insoluble in pH neutral solutions. Now, aluminum is the one metal hydroxide that you should remember that does this. So how does this work? So aluminum, as we learn in chapter 17, is inherently acidic. It's a small, highly charged metal ion. Remember, it was Al3 plus and Fe3 plus that we were supposed to remember. So here we have hydrated aluminum. So it forms a complex ion with the water, and that's what we said really all of the metal ions do when they're in solution. It's not just aluminum by itself, it's aluminum with some waters around it. These are acting as Lewis acids, donating electrons to the Lewis acids, Lewis bases. I get those mixed up. Lewis bases. The water's acting as a Lewis base. So if we take this and we put it in water, this thing here is an acid, and so it will give a hydrogen ion to the water. So this is an acid. This is confusing. I am not going to lie. So this is an acid, and it can act as an acid in the water. And so it's giving one of its hydrogen ions to the water to make the hydronium ion. So then what we end up with is 5 water molecules and 1 hydroxide, because this is the one that lost the hydrogen. Now the overall charge is 2 plus because that's an OH minus. Any questions right there? It's confusing. It really is. If we add more base, well, water is acting as a base here, but what if we add a really strong base like hydroxide? Well, that's going to pull off more of these. This is going to continue to act as an acid. So we've got this guy, now we're adding hydroxide to it, that's going to pull off another hydrogen ion. And so now we've got OH2, and the hydroxide ion became a water molecule. Lots of hydroxide present. This can happen again. And so this is one of these. It's going to donate its hydrogen to the water, to the hydroxide, making water, and we'll end up with this. Now, this is now neutral in charge. This guy was an ion, this guy's an ion, that guy's an ion. Those ions are soluble. This neutral compound is not. This is equivalent to AlOH3. So remember, water you can kind of put in or take out of the equations that happen in aqueous solution. Water is doing a lot of stuff behind the scenes. We don't necessarily have to write it all down or look at it, but it's there. So going from this to that, we're just removing those water molecules. Okay. If we take this and we add more base, what's going to happen? Well, we're going to have another hydrogen ion from one of these water molecule ligands go over here, and now we're going to form AlH2O2 OH2 minus. Wait. I think there's another typo there. Pretty sure this should be 4. Because we had 3 waters, now we have 2. What happened to the 1? Well, it became a hydroxide. So this goes from 3 to 4, and this, the hydrogen from this one and that hydroxide is what makes the water. I am not going to make you write this out on an exam. I will expect you to know that aluminum is soluble at high pH and low pH, and insoluble at neutral pH. I'm explaining to you why that is, and you need to follow along well enough that you believe me, and then we'll call it good, okay? Because there's a lot of times where, it's like, okay, so-and-so explained this big, complicated, political thing to me, and I understood what they were saying, and so I believe their conclusion. Can I explain that to you? No. Do I still believe what they said? Was I convinced by their explanation? Yeah, I'm going to hold on to that because I know there was a rational explanation. Can I explain it to you? No, I can't because I haven't studied it that much. Okay? This is not something that we need to spend tons and tons of time on remembering. But we should be able to follow when I explain it. Okay, so here we have aluminum. So at low pH, we are going to have aluminum be soluble. It's going to be this AlH2O6 3+. This can act as an acid, donating hydrogen ions, but here it's not going to act as an acid because it's already in an acidic solution, so it's just going to be itself and it's going to be soluble. When we go to pH neutral, now we're going to get, this is going to do its thing, acting as an acid, donating hydrogen ions, and making water molecules. And so then we're going to end up with AlH2O3 OH3, which can also be called AlOH3. So that's where the aluminum hydroxide is. This is pH neutral. You look in the table, aluminum hydroxide is not soluble according to the solubility rules. At low pH, it is soluble. At high pH, it's also soluble because it will continue to donate hydrogen ions to the hydroxide and become an ion again. Weird, huh? We're actually going to use this in our qual scheme, or qualitative analysis scheme, for aluminum. We can precipitate some other things out when we're in an acidic solution, and then we can precipitate out the aluminum by taking that solution and making it pH neutral. If there's aluminum present, it will precipitate out. So aluminum is not the only one that does this. Chromium 3+, zinc 2+, lead 2+, tin 2+ also do that. And so the extent to which a metal hydroxide dissolves in, I'm not asking to access the camera. The extent to which it will dissolve in both acid and base solutions depends on how amphoteric it is. I do not expect you to remember these other guys. They could show up in homework problems. For an exam, I do want you to know that aluminum does this. Okay? I can pretty much guarantee there's going to be a question on the next exam.